This year's Nobel Prize in Physics is about science at the time scale of attoseconds. And what you see here is an attosecond related to 1 second, which is approximately the heartbeat. And the ratio of 1 second to an attosecond is the same as the ratio of the age of the universe expressed in seconds to 1 second. And as Professor Olsson explained, we are now in the world of electrons. And let me remind you, electrons are not only working in gadgets like this. They are working in your full body. Chemical reactions are controlled by electrons, and they move on a time scale of attoseconds. This is the beginning. This was an experiment carried out in Paris-Saclay in 1987 by Nobel laureate Anne Lullier and co-workers. And what they did here was they took a very powerful infrared laser and shine it through a gas jet of neon or argon or xenon. And then they looked at the photons coming out from this interaction with a spectrometer, as you can see here. So this is actually the original drawing of their experiment in the 1980s. So what did they see? Well, they saw a number of, the laser has a base frequency. It's about 1,000 nanometer in wavelength. And they saw overtones of this frequency, a large number of overtones. And the overtones first fell off quite rapidly, and then came a long plateau, and then a cutoff. So the question was, what is generating this plateau, and how can it be exploited? And Anne Lullier in particular worked for a decade with different theoretical and experimental methods to understand what this plateau can be used for and how to explain it. So in order to generate very short pulses, you need all these different overtones. And I will illustrate this now by assuming that we have a number of light. We have light with different frequencies. As you can see here, light with different frequencies. And if we now let these different frequencies interact and interfere, what can happen is that they interfere in such a way that at certain points we create an amplification, whereas at many other points there is destructive interference, nothing happens. And what you get is a pulse train of attosecond pulses. So the trick is really to sum up many different overtones. That gives you the bandwidth. But that's for one atom. Now we are talking about several atoms, and several atoms must work together in phase. Otherwise, it won't work. And it's the same with the symphony orchestra. If each member of the orchestra would be playing whatever they want, the audience would just experience noise. But if they play in sync, and of course you have the conductor making them play in sync, then we get music. And it's the same with the atoms. They have to work in sync. And this was figured out by Anne Lullier and others, how to do this.